Hello, my name is Zhaokai. I'm a recent graduate PhD from Rutgers University, and I'm now teaching accounting in Marist College. So today I'm going to give you an overview of the regression analysis in Audit. So basically in regression, the main goal is to find a line that goes through all these data points that regression line can best describe the relation between the independent variable x and the dependent variable y. So a regression regression line can be best described as an equation here, y hat equals to b0 plus b1 times x, where b0 denotes the intercept and b1 denotes the slope. And the way to calculate that is through a method called ordinary least squares, or OLS, where this algorithm will minimize this distance of these observations to this line here. So once we have calculated this regression line here, one way to check how well our model did is through R-square, where the R-square, the higher the R-square is, the better our model is. And R-square basically tells you how much percentage of the variation in Y can be described by our model. There's another way to measure the how well we did with the model is through residuals and standard error of the estimates. So basically, the residual is a difference between the actual value y and the estimated value y hat. And standard error of estimates represents how much error we are making on average every time we are making a prediction or estimation. So this simple linear regression can be extended to multiple variables. So when we have the second independent variable, x2, the only thing we need is to add another slope, sb2, for the second independent variable, x2. And we can even further extend that to multiple variables as long as we add a coefficient for each independent variable. So besides those linear regression, we also have different types of regression, like logistic regression, where we have y, our dependent variable, to be binary. It's 0 or 1. So 0 means the failure of event, 1 means the success of an event. So logistic regression can be used to estimate the probability of the success and failure of an event. Polynomial regression is where we have the power of independent variable is more than 1, or we can say it's a curve function. So in linear regression, we assume the relation between x and y is linear, but in polynomial, it can deal with those curved functions. Stepwise regression can be used when there are multiple independent variables to pick the most important ones. Ordinary regression and Poisson regression are used when this data includes special category like ranked values or counted data. So auditors generally use regression for two purposes. The first one is to regression can be applied for this analytical procedure. So analytical procedure are used for substantive testing, planning, and financial statement review. And auditors can use regression to identify unusual fluctuations from expected norms in substantive testing. And auditors use regression through two ways. First one is to examine whether the coefficient calculated is inconsistent with intuition. So for example, we think that the more employees a company have, the more revenue the company will make. However, if the auditor find a negative coefficient between employees and revenue, then that may be a red flag. The second is auditors can use regression to identify outliers with residuals. So an example looks like this, where you look at this scatter plot, where we put two standard errors as the threshold to find all those values that is outside the 95% probability, and those numbers can be identified as outlier by the auditors. So that concludes my demonstration video. If you are interested, feel free to watch the full video. Hello, my name is Zhaokai. I'm a recent graduate, a PhD from Rutgers University, and I'm now teaching accounting in Marist College. Today, I'm going to talk with you about this regression analysis in audit. Speaking of regression, especially simple regression, everything starts with two variables, one called independent variable x, the other called dependent variable y. So an independent variable x marks as the input of the models. So they are controlled inputs. The dependent variable y marks the output or the outcome of the model. So for example, if you see on the slides, you can use floor area as the input to estimate the output y as a store revenue. And this, in the simple linear regression, we assume that the relationship between the dependent variable and independent variable is linear. So let's take a look at what the regression algorithm does to open the black box of the algorithm. So everything starts here from the scatter plot. Here we have this x-axis as the independent variable, the horizontal axis, and we have a vertical axis y marks the dependent variable. So all those dots on the scatter plots represents our observations. So the goal of regression is to find a regression line that goes through all these dots that can best describe the relationship between the independent variable x and the dependent variable y. So based on the different types of relation, if the increase of x leads to an increase of y, we have a positive relation. On the other hand, if the increase of x leads to a decrease of y, we have a negative relation. So a regression line can usually be presented as use the formula equation y hat equals to b0 plus b1 times x. Y hat denotes the estimation. So in statistics, if we use y, we represent the actual value. Y hat with a little hat on the letter y means the estimation. So estimation equals to b0 plus b1 times x, where b0 denotes intercept. Intercept is the beginning part of where the regression line starts from the y-axis, and b1 represents the slope. If it is a positive relation, then b1 will be larger than 0, as we can see in this example. Or if it is a negative relation, b1 will be a negative value. So for us to find the regression line, the method we use here is called ordinary least squares, or OLS. So what this method does is basically it tries to minimize all those distance from those y to our regression line. So the final outcome of our regression line will have a minimized distance to each of the dots you see here on the scatter plot. So I'm going to introduce with you the OLS through an example. So in this example, we can see 10 stores where we have two variables. X, the input, represents the number of employees in each store, and Y, the output, represents the revenue in thousands. So we can see there are 10 stores here, and each of them have some numbers of employees, and they also have different revenue in thousands. So to form the regression, the first thing we do is plot them on a scatter plot. So again, the horizontal axis represents the independent variable, the number of employees, and the vertical axis represents the dependent variable, revenue. So these dots here, we can see they are observations where we have, for example, the first dot represents two employees with 40,000 of revenue. So each dot here represents a store, and we can see that there are two stores, they have the same number of employees, 6, but they have different revenue here. So if you remember, our goal here is to find the regression line that passes through all these dots and can best describe their relation here. So to find the line, it's basically we need to calculate the intercept b0 and coefficient b1. And to do that, the first step is to calculate the average of x and average of y, or x bar and y bar. As you can see, with a little hyphen above the letter means the average. The way to read that is the letter n bar. So x bar represents the average of x, which equals to 10, and y bar represents the average of the y values here, which is 158.9. So once we have calculated those average, we can put them on a slide here. So we can draw first a horizontal line. A vertical line represents x bar equals to 10. So average of x equals to 10. We have a line here, and we can draw a horizontal line here represents y bar equals to 158.9. So you can easily find that these two lines cross each other with this point here, where x equals to 10 and y equals to 158.9. So this dot here is our starting point. So basically, one important assumption in OLS is any regression line we draw from here, we draw for this data set must pass this data. So any line you can draw, it needs to go through this red dot here. So with this as our starting point, now we only need to calculate the coefficient b1. So because it definitely passed through the line, if we can fix its slope, then we can get the line. So to calculate that, we can use some models proved by the statisticians. So our starting point will be first to find all those observations, the distance of each observations to the average of x bar, so 10. So we find the distance between each observation and the x bar. And we can do the same thing from each observation. They also have a distance from its position to the y bar here. So to show you on the mathematical calculation, we can calculate x minus x bar and y minus y bar just with the using the number in x minus x bar. In this way, we can calculate that. So to get our coefficient b1, we can easily use this formula that's proved by the statisticians. If we do calculate numbers in this way, we can minimize their distance from the points to the line. So what you can see here, this equation where sigma represents the sum. So the sum of x minus x bar times y minus y bar, and the sum of the power of x minus x bar. So we can calculate each single number of x minus x bar to the power of 2 and x minus x bar times y minus y bar. And then if we sum them up, we can get the numerator and the denominator. So after the calculation, we put the numbers in the formula, we can get b1, which equals to 11.99. So that means we calculate our coefficient to be 11.99. So once we get b1, it's fairly easy to calculate intercept, where we can just, because we know that this regression line must pass through the average value. So we can put b1 in the equation and then put x equals to 10 and y hat equals to 158.9 in the equation, and easily we can calculate b0 equals to 38.96. So from the previous calculation, we can calculate the regression line here, and we plot that on a scatter plot. So we get the regression line. Did we finish everything? Not yet, because we also need a way to measure how well we are doing with the model here. So the first measurement we are using is called R-square. So basically R-square, this is the formula for R-square. So R-square measures how good the relationship between the independent variable and the dependent variable can be described by our regression model. So R-square, it's fairly easy to calculate. again, the sigma here represents the sum of all those numbers. So the y hat is our estimated value, as you can see here, the green dots on our regression line. So if we put the number of x in our regression model, and you can get the estimated value y hat. So y hat, we measure the distance from y hat to our average of y bar. We can get the distance. And then if you square that and sum everything up, so that part measures amount of variance of y that can be explained by our model. Now, speaking of the denominator, where we look at the y minus y bar is the distance from the actual value y to the average of y bar. And if we square that and sum them up, we can calculate the total variance of the model. So basically, the R square, what R square is telling us is how much percentage of the variance of y can be explained by our model. So put them into calculation, we can get y minus y bar to the square of y minus y bar fairly easy. We can just use y minus y bar and take the square of that. To get y hat, we just put the number of x into our regression model. We can get y hat, and then calculate y hat minus y bar to the square of 2. So put the numbers in our R square formula. We can calculate R square equals to 92.01%. So this R square here means that a few things can be interpreted from this R square. So first, our model can explain 92.01% of the variation of the observation, the sales revenue. Or we can say that our model is describe a major part of the relationship between dependent variable revenue and the independent variable number of employees. So basically, the higher the R square is, the better the model is. And if you ever see an R square with so high that's almost equals to 100%, you will see our observations to be very close to our regression line. On the other hand, if you observe a very low R square, let's say R square equals to 1%, then you probably will see the observations dot all over the place. And basically that is saying our regression model is not a good indicator of the relation between independent variable and dependent variable. So another way, so R square serves as a way to measure the overall regression model. Another way to measure all those single, how our model is doing with these single dots is called residuals and standard error of the estimates. So again, here is our regression line, and if we put the x number in the model, we can get our y hat, our estimated value. So the blue dot here is the actual value, and the green dot here is the estimated value. So if we use y minus y hat, what we are calculating here is the model's errors or residuals. So basically, it is saying the distance between the actual value and the estimated value. We can plot them, we can calculate them in from here, just use y minus y hat, we can calculate the residuals. And we can even plot the residuals on the scatter plot. So this is what we call a residual plot, where x is the number of employees and y is the residuals. So another assumption here in OLS is these residuals should be not in a relation with x, meaning with the increase or decrease of x, we should not examine any patterns. So if the pattern looks like this here in the slides, the dots are all over the place, that means we have a good regression model. So another way to calculate that how much error we are making every time we make an estimation is called standard error of the estimation. So the way we calculate that is use take the square root of the sum of y minus y hat, get the square, and divide it by n minus 2. So n minus 2 refers to the freedom or degree of freedom. So what this number here tells us, the result of standard error of estimates means how much error we are making every time we are making an estimation based on the regression model. So for example, if we estimate that if we use the regression model to estimate a store with 10 employees, then on average, we are making an error of $15.69 thousand. So that's the standard error of estimates. So to summarize what we have learned in this regression model and in the simple linear regression model is we have calculated B1, the intercept, B1, the slope, B0, the intercept, and also we get the regression line. Also, we calculated R-square and standard error. And fortunately, in today, we don't need to calculate this by hand. We can easily use those data analytics software that can automate the calculation for us. So I'm going to introduce you with an example in Excel. So if you open Excel, and you can find under the Data tab, we have a Data Analysis option. Click on that, and you can find the regression in this window. Select the regression, click on OK, and we can proceed to the next one. So this window will pop up once you click on the regression and click on OK. So the input section here needs you to specify where the data is. So on the Excel sheet, the input of y represents your outcome or the dependent variable, so you just select y, the range of y, and the input of x is the number of employees or your independent variable. If you have multiple x, you can include that in this area. And then this label means if you have a name for the variable, that's you check that. If it starts directly without any name, you can uncheck that. So in this case, we have the name for both of the variables, so we check that. Constant is 0. This option means do we want to set interception B0 as 0. So if we set this, that means our regression line will start from 0 and 0 from that point. So usually we don't check that. The confidence level here means if you want to view confidence level other than 95%. So by default, Excel will show us confidence level at 95%. If you want to see some other numbers, you can check that and put in the desired percentage number. So output option here means where you want your output to be. You can select a specific cell or a new worksheet or even a new workbook. The residuals part lets us to get some information on the residuals, whether you want the residuals to be calculated, whether we want to plot the residual plot and the line fit plots. So check what you want, and we can click on OK to get the result. So the result from Excel looks like following. We have the result as you can see in this slide, and also I put our result also manually calculated result on this slide also, so that we can compare these two sets of result. So the starting point here is R-square. So we can see there are 3 types of R-squares in Excel. But the main thing we are focusing on here is called adjusted R-square. Adjusted means this R-square has been adjusted for the number of variables. So if you compare this adjusted R-square to our R-square, you can see that these two numbers are exactly the same. And also we check our standard error, which is 15.69. It's almost the same as we calculated. And then it tells you our observation is 10, so we have 10 stores. So the next table in Excel is called ANOVA, or Analysis of Variance. So in this part, we are going to get some information of the overall model based on our calculation here. So SS here stands for sum of squares. So we have the SS for three things. First, the sum of squares of the regression model, which is the part of variation that can be explained by the model, or SSR. Then we have sum of squares for the residuals, or the SSE, sum of squares of errors. That's the part of unexplained variance. And finally, if we include both explained variations and unexplained variations, we can get this total variation. So that's the SST, sum of squares of total variations. So as a matter of fact, if you use explained variation SSR divided by the total variation SST, you can calculate R square. Mean square stands for the squared mean. And this F statistics here, F test, shows whether our model is significantly different from a default model. So the default model is, instead of calculating this regression formula, we can easily say whatever the X amount is, Y always equals to average of Y. So Y equals to Y hat, no matter how X moves. So this F test here is to test whether our model is significantly different from that default model. So the way to interpret this result here is we look at the number under F and the number of significance F. If you find the F score is significantly higher than the significance F, that means our model is significant, which means our model is has some meaningful insights in that. And finally, this coefficient table tells you the number of B0 and B1. So let's look at the intercept first. So the coefficient of intercept is B0, 38.96, the same as we calculated. And the coefficient of X is B1, which is 11.99, the same as we calculated. So this 11.99 means for every one increase in the number of employee, we have 11.99 thousand of revenue increase. So we also have some other things here, like the p-value. So this p-value of X is important because it describes how much percentage that we are obtaining this result based on pure luck. So generally speaking, we want a small p-value to make this variable significant. And there's no general way how we describe that. There are only some rule of thumb. So the threshold of p-value can be set as 1%, 5%, or 10% based on different situations. So we have just talked about the simple linear regression where we have one dependent variable and one independent variable, and using ordinary least square. And in fact, we can extend this model to incorporate multiple variables. So for example, if there are two independent variables, x1 and x2, what we calculate here will be a regression plane, and we can develop that by adding another slope, like b2, to the second independent variable, x2. And we can even extend this model into multiple variables, although we cannot visualize that. We can have a model as long as we add a slope for the x, we can extend that to incorporate multiple variables. So there are also other types of regression where we can use. For example, logistic regression. So the logistic regression is used to find the probability of success and failure of an event. So the y here can be a 0 or 1. 0 means the event failed, 1 means the event succeed. So using logistic regression, we can use input to estimate whether this y will be a success, the event will be a success or not. Polynomial regression means the power of independent variable is more than 1. So in linear regression, what we assume that it's a linear relation. So the maximum power of x can be only 1. But in polynomial regression, we can set the power of x to more than 1. So one thing we need to pay attention here is not to underfitting or overfitting the model. Underfitting here means we are trying to describe the relation between x and y with a too simple model, and overfitting means we are using a model that is too complicated to describe the relation. What we need to do is a model that is just right, and there are some ways to achieve the optimum solution. Other regressions, we have stepwise regression, where in the case we have multiple variables, we can use stepwise regression to choose the most important variables to be included in the model. And in ordinal regression and Poisson regression, where we have special data point. So a major fact of assumption in regression is the normal distribution of the data. However, when we have special types of data, for example, ranked values or count data, we need to make other assumptions, and that's why we need these different types of regression to deal with data in those special occasions. So we just finished describe those different types of regression, and finally I'm going to introduce you this little application of regression in auditing. So auditors can apply regression for analytical procedures, and especially for substantive testing, where auditors can use regression to identify unusual fluctuations from expected norms. So there are two approaches to implement regression. The first one is to examine whether the coefficient is inconsistent with intuition. So for example, generally speaking, we should expect more revenue when the store has more employees. So that means intuitively, we believe the relationship between the number of employees and the revenue should be positive. However, when auditors use the regression model and find there's a negative coefficient, that can be a red flag, which should raise concerns for auditors, and they should perform further examination. And the second way is to use regression for auditors is to identify outliers with residuals. So giving you a simple case here, what we have here is data for 3 consecutive years. So in the period of 2009 and 2010, they are the base data for the previous 2 years. And what the auditors are looking at is current year's data at 2011. And this data has 2 variables, one called sales, the other one called cost. So the first step is to build a base model using the previous 2 years' data. So from here, we can see that using the cost of sales as independent variable and the sales number as the dependent variable, we can easily build this regression model that we find a positive relation between x and y. And then the next what we can do here is to plot the current data into this regression model. As you can see there, this current data is plotted as those red axis or red marks, where it's kind of fit into the flow of the regression line here. So we can say, all right, that passed the first one, because we see for current year still an increase of cost will lead to an increase of sales. So that part fits our intuition. Now the second part is to use that for to detect outliers. So what we are going to use here is called residuals, using recorded value minus estimated value. So just to refresh memories on residuals, we have regression line y equals to a plus bx, and then if you put the x number in the regression, you can get the estimation y hat, and we have a recorded value or the actual value y, and the distance between the recorded value y and the regression estimation y hat is called residual. So to use residual to identify outliers, auditor can set a threshold based on a few factors, such as materiality, designed degree of confidence, or statistic characteristics of the model. So basically anything that's any recorded value that's above the threshold, and also be aware that threshold can be both positive and negative. So if a recorded value exceeds the threshold, it will be identified as an outlier. And the part where how much the recorded value exceed the threshold can be marked as excess. So just use YT minus threshold. So that will also give us a dimension of a description of how much different is the recorded value Y as compared to the threshold. So finally to give an example here is what you see here is the same regression model we built. However, we put a threshold that is within two standard errors. So based on this normal distribution model, where two standard deviation represents 95% of the probability. In other words, if we are going to examine a data, it should be 95% probability within the range. So adding those two into this regression model, we can find that a majority of the new observation in current year, they are within the range, and there are two dots there. Those X there seems like outlier. So that two dots can be used by auditors marked as red flag for further investigation. So that concludes my presentation. Thank you.